derived... Okay.
Just explain me what's here.
At the very top, we have some elementary laws, this first row, which we're going to build everything off of. And here you can see the covariance vector relation to the metric tensor times a contravariance vector. We have similar things here. All we did was apply the inverse. This is saying that if we have two metric tensors, one with all its components upstairs and one with its downstairs, and they share a common component, that we can just express it as the Kronecker delta with mu on the top, and I drew this as a v, but it's supposed to be nu. This is a fundamental rule for partials. Now after that, so these are kind of, I guess you could call them axioms or something. And after that, we can derive all of these laws. I had to erase this one because I made a mistake. Can't erase on this board. We have a bunch of different laws for tensor transformation. Here we have, if you want to transform from a tensor with all its components downstairs, which is the one which you normally learn first. Mm-hmm. Most of these, which you see here, actually all of these, are rank 2 tensors, which are going to be expressed in the form of a matrix. And for example, with all of its components downstairs, this is the one that you normally learn first. If we have alpha, beta component of this is just the alpha row and column. Or maybe the other way around. I didn't pay attention to how I worded that. And then we can, from there, build very many, these are not obviously all of them, transformation laws for how the components should transform. And also mixed tensors in terms of the contravariance metric, things like that. After that, we go into what the definitions of contravariance and covariance are in the context of normal vectors. These are the vectors which you learn about. They're your x, I hats plus y, j hats, things like this. I should point out the notation might be a bit confusing. When I have, for example, in this partial, x to the alpha, that's not saying x to the alpha. That's, yes. For example, x to the 2 would be y. X to the 1 would be the normal x to the 3 would be z. So that's just how we express the components. And similar things. If we have prime, that's our new coordinate system. That's if we changed it. So you can also define, this is when it has its component upstairs, that's contravariance, and then from contravariance we can also define covariance. And all of that is defined from the ordinary vector. The ordinary vector being what you would see normally. And the way we derive this h, it comes from the metric tensor. And you can see here I've written it down. A specific component mu nu of the metric tensor. Since in orthogonal vector spaces like x, y, z, cylindrical, spherical, the metric tensor will only be diagonal. All of the off-diagonal components will be 0. We can express this, that reminds me of the Kronecker delta. So we can use that, and since Kronecker delta only applies 1s and 0s, we also have to use a sort of scalar which we can apply to each row, and we denote that's actually column, and we denote that h, and then the row number will be mu, and then squared because we're going to take the square root here. And then we also have, these two are saying equivalent things, just you have to plug in the formula. This is just the general one, and then this is when you apply it, you find that's the general pattern. And then finally here we have basic tensor algebra laws. So this is scalar multiplication, and it says that if we have, I should first introduce what rank is. The rank of a tensor, for example, a scalar is a rank 0 tensor, a vector is a rank 1, and a
generalization of vectors.
Matrix is
rank 2.
Rank 2, and after that we don't really have words, and it's denoted this A plus B. However, many are upstairs and downstairs. For example, all of these which we've seen so far are gonna be rank 2, so they're gonna be matrices. However, this one, which I put at the end, it's rank 4. So here we can see the most simple type, which is scalar multiplication. It basically says you multiply all components of the matrix by this scalar, and you get the new. It's literally just the matrix laws. We can also add components to get a new one. That's tensor addition. This is called contraction because we're converting from rank 4 in total to just rank 2. And this only works if they have this common factor here, which I denoted as gamma.
But what's the intuition that it's just like, because
well, you have to, this is
for the first and second one it's pretty clear, but for the third
yes.
one, what is this?
Well, that's what's tricky, because unlike downstairs are very intuitive. You can just think of them as matrices. But these upstairs are pretty much rigidly defined simply by these definitions which we can derive. And then from there you simply plug in. And a similar thing happens here because we have all upstairs. And that's pretty much all of the laws. And I didn't include any of the derivations, obviously, because there's a lot of formulas.
Thanks for coming to my TED Talk about tensors.
Haha.
Very good. Sve si ovo danas radio?
Yes.
Sve ovo?
Yes.
Kad si počeo?
This morning.
This morning. Very good.
And I also finished chapter 6. I wanted to show you what I did yesterday, because that's the interesting thing.
Daj mi pokaži.
Yesterday.
Gde ti knjiga?
Huh? No, in Tensor.
Aha.
So, a few days ago,